Thank you very much for having me here. I really appreciated all the talks and things that I've learned this day. So I hope I will also explain you a few things. And this is all work done in collaboration with Carlos Ramos, that is my PhD in Barcelona, Stefano, that was my postdoc during some time. And then this is one of the chapters. The other chapter was initiated when I was working with Jacopo Surace, that was at that time my PhD in Glasgow. And then it was taken over with the collaboration with people from Max Planck and basically Miguel Frias Perez, that is a PhD student, and Mari Carmen Bañuls, that is a colleague and friend of mine there. I'm based at CSIC, that is a Spanish National Research Council. Okay. So I would like to discuss today if you can actually break the entanglement barrier, and I will tell you what I mean by entanglement barrier in one dimension when trying to look at the expectation value of local observable as they evolve in time. And so the short answer is yes, indeed, if you somehow try to exploit the idea that we have heard this morning in the context of ETH locally, and I will tell you how you can do that. And so basically the idea is that you want to trade this long-range correlation for some mixture, and you find here the first reference. And no, on the other hand, if you just try to use other tricks that people have been developing in the field, like this simple space-time duality. So and causal code, and this is written in this part here. So basically, the two chapters have two messages. The first message is I will introduce a new tensor network algorithm that takes a matrix product state that is kind of the evolution in time of your system, and somehow identify some correlation that we believe are long range, and use them to construct a mixed state that locally have exactly the same expectation value of local operator, but this is done in time and variationally somehow. So there is no a priori ansatz, so we try to kind of extract this structure as time goes by. And the other one is that I will bound what is called temporal entanglement, that maybe not of you are familiar with some growth of operator entanglement, that is another object maybe you're not familiar with. And I will show that since we believe that in the generic case, the operator entanglement scale exponentially with time, also this temporal entanglement will scale exponentially with time, and as a result, going just to this kind of temporal picture doesn't really help in generic case. Okay, so I will start with some brief introduction, and obviously the reason we are all interested in out of equilibrium dynamics is because we hope that out of equilibrium we can see properties of matter that we don't see at equilibrium. The idea is, for example, this simple picture. So we are all interested in getting high temperature superconductors. But due to the equilibrium law of physics, these high temperature superconductors, so the superconductors are kind of only live at below certain critical temperature and critical field. And the idea is maybe if we manage to devise a certain out of equilibrium protocol, we could extend the range of existence of this material beyond the law of equilibrium. Okay, but so this talk would be mainly using a tool that are called tensor networks. So I just sketch you the basic ingredients. So the basic ingredients of tensor network are obviously tensors, and the simple tensor is just vector. And so in all my drawings, tensors are represented by geometric shape with dangling legs, and these legs stand for their indices. So for example, a matrix has two dangling legs, whether a vector has just one single dangling eggs, and this would be a rank 3 tensor. And then whenever you see two geometric shapes connected by a line, so that's the kind of graphical notation for the formula in which you would contract those tensors over that index. So drawings are formulas, so please keep this dictionary in mind. So for example, imagine you have a state of a large quantum many-body system with n constituents. So you would have an exponential large tensor of coefficient, and the idea is that you can try to represent it as a tensor network, so a contraction of small elementary tensors that somehow would, once you contract them together, they would give you this big, larger tensor. Okay, and hopefully this tensor has some properties that allow you to actually perform these contractions, so they are small enough that you can deal with them rather than the big object. Okay, so now let me briefly remind you what we mean by entanglement barrier, and I would like to convince you that maybe it's more of a psychological barrier than a real one, but let me try to drive you through. So I'm interested in this case, only one-dimensional system described by local Hamiltonians, so sum of local terms. And then the idea is that you want to look what happens when you evolve them in time. So you have this Hamiltonian, you generate this big unitary, there is a large unitary in the Hilbert space, in the full Hilbert space, and you look at what happens when they evolve in time, but you focus on the expectation value of local operators in this talk. I focus on that. And so basically what you want to do is to compute this kind of object. You have some initial state that is not an equilibrium state, then you have some evolved operator, and you want to take the kind of expectation value of that evolved operator into your state. Okay, this is the kind of object that I will study today. And so in certain approximation that I don't want to go in, but basically the fact that you have a local Hamiltonian means that you can write that large evolution operator as a sequence of, almost infinite sequence of operators that have this tensor network form, in which every of this tensor has a finite dimension. So here, obviously, up and down, we have the dimension of the Hilbert space. So if you have spin 1/2, this is an operator that acts on n spin 1/2. But then the main important thing is that this leg here is also finite if your Hamiltonian is a short range in certain approximation that I won't go into. But in principle, you can get for an infinitesimal step of your evolution such an approximation, such an operator. And so the object that we wanted to discuss today just takes the form of this two-dimensional tensor network contraction. Okay, so you have time that goes in this direction, space that goes in this direction. In this case, I decided to have a product state, initial state here, and then I evolve it for some time, this u of t, and then I plug in the local operator, and I just take the complex conjugate. Okay, so that's the object that we would like to somehow contract in order to get a handle to this expectation value at time t. And now the traditional way has been to kind of pile this tensor up in columns and define actually the evolved state, psi of t, as a state made by what we call a matrix product state, where these matrices are just a collection of these vertical tensors. Okay? And so actually the question here is, what is the computational cost to perform such a computation in that way? And then the idea is that if you increase time, so if you add one layer, you immediately see that your matrix product state gets an extra leg, meaning that the size of the matrix naively explode exponentially with time, right? So we have a tensor product of these legs, so the size is just d to the t, where t is now our time, right? So it's explode exponentially. Then you can ask yourself, well, can I compress this? But actually, the bad message that was already kind of written in this paper in 2005 by Kavli and Calabrese is that one, in principle, think that can compress something when there is a kind of small entropy. But if you look at how this entropy evolves in time, and here we have a region of larger and larger number of spin in an infinite system, so 20, 40, 60, and 100, you see that the entropy always grows until a value that is compatible with the volume of your system, and then it saturates. But if you look at an infinitely large system, the entropy would continue growing forever. And so that's what we call entanglement barrier, because since the entropy grows linearly in time, and we have to accommodate this entropy in these two kind of links in our matrix product state, by definition the entropy is upper bounded by the number of links that connect my region with the rest of the system, and in this case is 2 times the logarithm of the dimension that I have on that specific Hilbert space. And it turns out then that this dimension that I showed before of this tensor should grow exponentially with time. And that is what we call entanglement barrier. So at some point, the entanglement is so large that our bond dimension should explode with time exponentially, and we have to stop our simulation, okay? The message I want to give today is that if you're interested in representing a local observable, maybe that's not the best strategy to go, right? So this entanglement barrier might be inherent to your choice of method rather than to the physics, okay? And so let me summarize one simple way to understand this growth of entanglement, and this is, again, was in this original paper by Cardi and Calabrese, in which you basically think of your Hamiltonian as having some pseudo-particle excitation that have a certain dispersion relation, and so wave package of those particles would move with the speed that is called the group velocity. That is just a derivative with respect to k or that dispersion relation. And so basically now you can explain the growth of entanglement by assuming that your state, since it's an out of equilibrium state, is a high energy state, and assuming that initially it's translational invariant, would have a large population of localized pseudoparticle initially that since the state is shortly correlated, they are only correlated very short distance. But then they start moving, and if nothing happened, this correlation is spread along the system. And so you can really kind of study this entropy picture by thinking, okay, now we have this left and right moving particles that are correlated. If I look at the region, at the beginning, all the correlated particles are inside, but as time goes by, there is one right particle that is correlated with something else on the left, there is one left particle that is correlated with something else on the right that enters my block, and this gives me one quantum of entanglement, and as time passes, these particles flow inside your block, right? And you get one quantum of entanglement for every particle until you reach the volume of your system, and then you get this steady state of particles that flow in one and the other direction. They're all entangled with something outside, and this means that your state becomes somehow highly entangled. So this is kind of a free particle picture, but in certain limit that I might discuss offline. If you want, it's valid also for a non-free particle. And so the idea that we had back in 2019 with my student Jacopo was to try to exploit this picture. And the consequence, so if you take seriously this picture, and you think, for example, of a single kind of entangled particle pairs that travel around your system, you might realize that whenever your particles are separated, one on the left and one on the right, from the region that so sorry, this is your system, this would be the entropy profile of a shortly correlated state at equilibrium. Then you have these particles that travel, and you realize that whenever they cross your system, your entropy increases by one bit, right? Because you have now have if you cut the system into two halves, you have a singlet. But locally, nothing really has changed, right? They might have left some trace, but really there is no reason why locally the state is more complicated or more complex than the state I had before. So this is the kind of driving idea of all this work. And so we applied that idea in the context of free fermion in that paper that I show. I will now discuss the generalization that we did with Mari Carmen at Max Planck in Garchin and Miguel in the case of generic tensor networks. So this is now applicable beyond the free fermion's calculation that we did a few years ago. And again, the idea is very simple. So if you go into a frame in which you have a certain region S, a region on the left and a region on the right, the idea would be to kind of identify a situation in which correlation are only, so there are some correlation that if you cut your system into half, you would see them as entanglement, but if you focus on S, this correlation never touch S, and they are just connecting left with R without touching S, okay? So this is the idea. So I have some local Hilbert space for my region S, I have some Hilbert space for my left part of the chain, and I have some other Hilbert space for my right part of the chain, and I have now a tensors that talk to these three regions, right? And what I would like to do would be exactly to try to identify inside left and right those degrees of freedom that are correlated between them, so between left and right, so they are not products, so they are correlated between left and right, but they don't talk to the region, okay? And so how do I do that? Well, in general, that's not easy, because in general, while there might be such degrees of freedom, there might still be things that correlate left and the system or right and the system, so you have to kind of find out how to isolate the things. And the idea is to use an idea that was introduced in a different context by Di Frevitel, that is the idea of disentangling. And so the idea is you would like to kind of look for a unitary transformation, so a change of basis in your left and right Hilbert space separately, that would indeed find the basis in which you identify some part of the degrees of freedom of left and right that are just connected among themselves, and then you see you would have this tensor that only connects left with right, and another part of degrees of freedom that still are entangled between left system and right. And this we call it fast degree of freedom, because obviously these are kind of things that have traveled faster than the rest and have already left your region, and this we call them slow degrees of freedom. And in formula, you would like to find this unitary acting on the left, identity on S, and a unitary acting on the right, in such a way that you can factorize these kind of slow degrees of freedom from the fast one. Okay, so that's your aim. Sure, this is something that strongly depends on your state. So that's why you have to do it in a kind of variational fashion. So that's what I mean. So that's the idea is that you might be able to always find it, but you might be able also not to find that factorization. So you would look for it variationally. Okay, so that's the idea. And so let me before so showing you what happens if you try to do it in reality, let me derive the consequences. So let's assume that you have been able to do to have such factorization. What can you use it for? And the idea is that we can really use this factorization to construct a mixed state that has exactly the same reduced density matrix. So let me drive you through the calculation. So imagine that you manage to do such a factorization, and imagine that so whatever is on right is in a kind of orthonormal basis, whatever is on left here, it's on an orthonormal basis. So when I do the reduced density matrix of, for example, the system plus the left block, everything that is on the left cancel, right? Because this is just an orthonormal basis, and I'm left with this tensor network contraction. You see, I have the slow degrees of freedom, I have this unitary, I have some fast modes that connect to the fast mode, and then the unitary again. And the same is true on the other side. Okay, so we see that the reduced density matrix of the left and the right side take this form. But then what I can do, if I'm now interested only in things that are separated at most by size law, so I can just substitute my initial state by a mixed state, this mixed state here, that whenever I compute the reduced density matrix, this reduced density matrix for left and system and right of system will be identical to my previous one, but this is now a mixed state rather than a pure state. Okay, and so you see that I have obtained a kind of purification of my state. So I obtain a state that you have to think of it as a kind of, there are some ancillary degrees of freedom that need to be traced out in order to construct your density matrix. Okay, and so somehow you see this long range correlation, they were before coherent, now have been completely decohered, right? So I kind of projected all their coherence. And so let me see, so this is kind of the idea behind it. Let me show you how this actually works in practice. And so the idea is that we tested it on this generalized Ising model that has both a transverse field and the second nearest neighbor hopping, right? So we break integrability. So for j equal to 0, I am on the left, and for there are several values of my transverse field. Whether for j different from 0, I am on the right. And so what I'm plotting here is actually so I take this tensor, I change the basis in such a way that I have both slow and fast degrees of freedom, and I trace out both the system and the slow degrees of freedom. And if I manage to separate these fast degrees of freedom, this should become now a pure state and projector onto these fast degrees of freedom. Okay, and so what I'm plotting here is actually, for example, here, as time goes by, I try to find these unitaries variationally, and I don't explain how, but if you want offline, I'm happy to describe. So I try to find the best possible unitaries that does these things, and I look at the residual entropy between these fast and slow degrees of freedom. And you see that as time goes by, this entropy goes down basically exponentially. Okay, so the residual entropy between slow and fast degrees of freedom goes down exponentially. And obviously the speed at which it goes down depends on the specific quench. So there are quenches for which you have to wait more, there are quenches in which you are able to isolate it fastly. These insets here represent different sides of your block. So obviously, as the block is larger, you have to wait longer for information to flow out of your block. So it's more costly. And here, what I have in these labels here represent the kind of amount of entanglement that is transported from left to right. And this is computed through what is called entanglement negativity. So now in principle, this state, since it's not a completely pure state, but is a mixed state because it still has some residual entropy with the short and local degrees of freedom. So the entanglement is quantified in terms of the negativity, and you see that we managed to kind of extract here. That's also the same inset. We managed to extract order 1 entanglement that connect so like a singlet that connect left and right, more or less, almost a singlet, right? 0.8, 0.6, half of a singlet, something like that. And here again, that's the same plot, right? But for the case of non-integral systems. So despite the fact that this method is inspired by this pseudoparticle picture, here you see the integrability breaking is 30% of my hopping, right? So it's not small. And I will show you the result. Okay, is it clear? So basically, the message of this slide is that if you try to disentangle fast degrees of freedom variationally and you wait long enough, typically you manage to get them pretty disentangled, or order 10 to the minus 3. And now you can, once you get them pretty disentangled, you can, yes. So all of this is already in the thermodynamic limit. I didn't say that, but it's already done in the thermodynamic limit.
Thanks. Another stupid question. So compared to your time scale that you have on these, so is that about what you call the fast time scale?
Well, exactly. So the fast time scale, we don't know what they are, right? So indeed, this would be a way to find those fast time scales.
But what you would get is that your fast time scale is of the order of, well, a few, right? One.
Yes, of 5 in hopping units, right? This is t divided by j, if you want. Yes, but this indeed would be a way to find if there is any fast time scale in your program. Okay, so that's the slide on the results that shows you that now if you actually use this algorithm, so this is the expectation value of a local operator. Here you see the line that you would get with the method that was mentioned in the previous talk, the ITBD, that is the kind of state of the art. I mean, it's the simplest one, it's not the state of the art, but it's the simplest tensor network algorithm. And you see that the expectation value of your local operator would deviate largely from what you expect at large time. Whether this one here is, you see there is an exact line, because that's an exactly solvable model, so we can know what the value is. There is an exact line, and if you zoom in, you see that ours is not exactly exact. So there are some small oscillation around the equilibrium point, but is very, very close. Okay, and so on the inset here, I show you what is the bond dimension. So our calculation is our calculation is basically performed with multiple states. So the numerical cost is a power of the bond dimension, typically 3 or 3, I think. So and then you see the TBD, you see that the bond dimension explodes, as we already knew, and then here we truncate it because we can go beyond a certain point with our computers. But here, on the other hand, you see that in our methods, the bond dimension oscillate around a value that is below 100, right? Because every time you have to wait a bit, so the bond dimension increases, but then you're able to isolate some of these fast degrees of freedom. You can put them into mixture, and so you basically divide your bond dimension by 2 again, and then it starts again. And so, and you see that, as I mentioned, there are some residual oscillation, so it's not exact, but we can extend the simulation up to 50 in order of j, and you could, as you see, the cost is just not increasing, so we could go forever, basically. Okay, and so here, so this was the integrable case. The non-integrable case is a bit more complicated. You see that now our result, so this line here is again the line, so we don't have any exact result here. We can compute the diagonal ensemble and put the line of what we believe should be the diagonal ensemble result here with other techniques that I will not describe. But then, as you see here, there is this residual entropy that we accept, and the larger the residual entropy, the shorter the time you need to let it evolve before truncating, so the cheaper the algorithm it is. So you see, if you accept some residual entropy of this amount here, you get the blue lines that is actually deviating from your exact result. But as your residual entropy gets smaller and smaller, then you see that your results approach what you expect is the exact thing, with some, again, small oscillation on the top. So obviously that's not exactly the result that you expect, but I'm pretty sure that if you try any reasonable extrapolation, you would get the result there. Okay. And again, here the computational cost might not be completely flat like here, but you see it's a very, very mild increase, probably not even logarithmic, so sub-logarithmic. I don't know. So since it oscillates, it's difficult to kind of extrapolate, but I would expect that this is a very easy to handle cost. Okay, with this, I only finished my first part. And so I will just give you the spoiler of the second part. So the spoiler was that, and let me tell that I did it with this Stefano, that was my postdoc, and Carlos. So the spoiler was that we started with a certain strategy, but a few years ago, people, and in particular Hastings, Ignacio Sirac, and Mari Carmen, suggested that a better way to perform the same contraction would be to take your tensor network, fold it, as you were doing a kind of path integral in a Keldysh contour, and then contract it in the other direction, right? That is called space-time duality. And then if you look at local operators, so now everything is double, so that's why I have two circles, because it's a two-folded tensor network. You can also simplify your calculation by taking into account the effect of a causal cone. So you now have to contract a triangular tensor network. And what they proposed was to construct an MPS in the time direction. It's called temporal MPS, okay? And so what we showed in our work is that if you slightly modify their construction by including actually the operator in your temporal MPS, and take into account that there is no complex conjugate in your calculation, so that so if you want to, let's say, if you want to compute the things at times t and time t plus dt, this network increases and the bond dimension increases, and you can ask what is the computational cost, right? And what we showed is that if you really take seriously this transition matrix where there is no complex conjugate and it's reduced transition matrices, you would get something that is called generalized entropy. That would be the spectrum of this object here, that for some other reason is now considered in the context of holography of the SCFT. But basically, the spectrum of this generalized entropy can be upper bounded by the spectrum, and I don't do the calculation, but the message is that by the spectrum of the operator entanglement. The operator entanglement is that the entanglement that you get if you treat your operator, the Heisenberg evolution of the operator, as again a matrix proof state. And again, here it's doubled because you have a Brian Ket. And so this paper by Prozen and Zdaric, thank you, shows that actually that operator entanglement behaves differently between integrable and non-integrable model. And so basically, the idea is that whenever the operator entanglement grows slowly, such in the case of integrable non-interacting model, then also the temporal entanglement would grow slowly, so as a power law of your time. But whenever the operator entanglement grows exponentially, like it is believed to happen in generic system, the temporal entanglement will also grow exponentially. And here you see that we have this operator entanglement for non-integrable model. For integrable model, this more or less grows as a power law because it is a logarithmic scale. This curves up, so it goes more or less exponentially. And you see that also this would be the temporal entanglement for different operators, because now we include several operators, so there is a band, and you can kind of look for the worst case. But you see that it actually follows what the operator entanglement does. And so the boundary is not completely saturated, but the behavior in time is the same. And so the take-home message is, by just doing space-time duality, if your system is non-integrable, so it's generic, probably you won't be able to overcome the entanglement barrier. So it's not the best strategy in this case. Okay, and so that's the summary of the talk. So I hope I convinced you that the entanglement barrier can be circumvented. The idea is to use a kind of a local version of ETH. So try to locally substitute your pure state by a mixed state that has the same property locally, and this can be done by identifying these 5 degrees of freedom. On the other hand, folding and temporal MPS alone might not be enough to overcome this temporal barrier, as our bound shows, in which indeed we show that the entanglement, the temporal entanglement can only be small if the operator entanglement is small. Okay, and so that's it.
Thank you. What is the cost of your disentangling algorithm?
So it depends. You can use several of them. So each one has a different cost. But basically, let me go to here. So you can either minimize the Schur norm between this tensor here and that one, and so this basically has a cost bond dimension d cube, or you could try to construct kind of Rényi entropies of this guy here, and so these are also has cost d cube, but it becomes very nonlinear in the unitary, so you have to typically linearize and iterate, and so I don't know. So we haven't really computed the cost of the number of iteration as function of the bond dimension. So this why I don't know, but each iteration costs the cube.
So as Mark explained to us today, basically eigenstate thermalization tells us that there's a lot of redundant information because nearby eigenstates don't contain any new information about local observables. Mm-hmm. So if I'm thinking about the entanglement barrier, I mean, that comes about because we try to capture everything, even if it doesn't really physically make a difference from the local point of view. So can your approach be also seen from that point of view, that you're kind of taking advantage of this feature in the context of overcoming the entanglement barrier? Sure, indeed. So you see, the only thing that I do is I maintain a certain reduced density matrix of my system. So I look for, actually, so you can see it the other way around. I look for a mixed state that has some reduced density matrix basically almost equal to the one that my pure state would have. And that's exactly what you say, right? So I'm kind of throwing away coherences, but these coherences should be far away from my block, right? So I kind of keep all the coherent information inside my block,
that I decide is S, and then I throw away these coordinates outside of my block. And indeed, information that I will only access if I would look at correlation separated of operators separated by more than my block, right? And that is the information that I throw away, basically.
Thank you for the nice talk. Is it correct to, I mean, there are some regime in the speed of the of the kind of dynamics that makes this approach better or worse applicable? And then the second question is that if there is something, some principle limiting or not the extension of this approach to two-dimensional system for some regime. Thanks.
Yes, thank you for the question. So here you see that clearly the time you have to wait before this flies away depends on your quench, right? And what we observed, and in free fermionic case is easy to understand why, is that if you quench across a phase transition, the dynamics is lower because you kind of populate a state that have very, very small velocity. So indeed, the fact that if in practice this method will be always able to help you, it clearly depends how much you have to wait until you're able to reduce your bond dimension, and if your simulation allows you to wait that long, right? Because sometimes you have to wait very, very long. And so that's an open question. The systems that we studied were always in the category in which this work, right? Possibly there will be cases in which they don't. With respect to two dimensions, I guess that I don't see any reason why this shouldn't work. It's just that one has to again formulate in terms of so now the difficulty of the things is that now your boundary between your region and the rest of the system is a one-dimensional object. So you will have to find some kind of disentangling scheme. So you would have to do something like a mirror on the boundary and try to separate again some short from fast degrees of freedom. I still don't have any kind of nice idea on how to do it in practice. So I think that in principle it should work. In practice you have to work a bit on the tensor network structure in order to get something that is contractible and useful again in such a way that you can try to do the same thing.
So if I remember correctly, when you have DMRG or tensor network methods, then you usually have some rigorous bounds that tell you that you will be converging within these bounds to the exact results. And now I wonder if you add something like this, which has a motivation, but it has also some heuristics to it. I mean, do you lose this guarantee, or can you like restore it by under the assumption of ETH, or do you know anything about this?
So, I mean, the only bound that I know for the MRG are in the static case, right? And then you can somehow argue that if you follow the exact evolution of your state, since you are representing the state exactly, so you can somehow match the truncation on your Schmidt values, so your bond dimension, to the error you are making in your state. So, but that indeed would require exponentially large resources. So that approach would require exponentially large resources. Now, how do you quantify the actually the how do you say the approximation that you are doing in this method is not clear indeed. So. I don't think we have any theorem that tells you that this should work, and how much the error on the local observer is related, for example, to the only error that you can measure, that is this residual entropy, right? So the only error we are making here is that we are assuming that this residual entropy is zero while it's still maybe 10 to the minus 3, right? That's the error that we make. And then it's an interesting question. Once you know that you have this 10 to the minus 3 error that you are making, right, how does it reflect on your things? But we still haven't figured out that. We just observed that whenever you manage to get it small enough, then you see this small residual oscillation onto the equilibrium state. In the non-integral case, and in the integral case, it seems that it goes towards the right direction if this error decreases, right? But we still don't have a kind of systematic understanding on this.
Are there any other questions? Okay, so let me ask one. So in this way, you're able to reproduce dynamics of local observables, let's say. So, but what if you want to do 2 times observables or
yeah, so
GOC?
I think that there actually this time thing would help, because what I just show is that if you just look at the expectation value of a single operator, then you have this problem of the temporal entanglement. But if you look at the expectation value of 2-point correlation, then there are these results by Adam Nahum on how the operator spreads and how it must refocus in time. And I think this would actually be enough so you could just use this temporal picture to compute correlation function, because you know that most of the time the operator won't spread too much if they have to refocus, right? And this means that you will be able to really cut your bond dimension of the MPS to a very small value, because you know that the large operator are the one that implies that the operator entanglement grows fast will not contribute. So I think that indeed, it depends on what you want to do. So for a higher order correlation function between local operator, the temporal contraction might help you a lot. Yes.
Can you actually use it as a diagnostic or a classifying tool for entanglement, that when such factorization is not possible, you have more quantum magic in your states or things like that?
Yeah, I have never thought about that, but it's interesting. We can maybe discuss a bit. Yes, definitely. So I don't know. Yes, I don't know the relation with magic, but definitely there is some assumption here going on that somehow the information is spread almost ballistically, and would be nice to actually. I believe that this idea should work much better for non-integral system than for integral one. But the fact that in non-integral system the information is spread diffusively and it also kind of fatten as it spreads, make this kind of approach a bit harder, as we saw. But I believe that must be a way to circumvent that. So I believe that this should actually work better in integral case than in non-integral case than in integral case, but that's not what we see. So that's something I have to understand.
Thanks. So if there are no other questions, we can thank Luca again.